Okay, so now we are going to start talking about Chapter 2, One-Dimensional Motion. One-dimensional motion. In physics, or in science in general, when we want to describe motion, we need to figure out what are the words that precisely describe the motion so that somebody else could reproduce it. Right? So it's not just, oh, it's goes, I mean, I can't even think of language without using the physics terms, but we need to figure out what those physics terms that describe the motion. And what I mean by that is, let's say that you're going out to play fetch with your pet rabbit. And if you throw an object to your pet, right, that object is going to go through the air. And how do I describe it? Not why it goes through the air. It goes through the air because you have thrown it, you pushed it with your hand. But what is it that what are the words I can use to describe the motion of the object as it flies through the air? For example, you can say that it goes up and then it comes down again, right? You can say that it goes, it follows a certain path, it goes a certain distance, right? That's the dotted line. Or you can say that the rabbit is a certain distance away from you, and so you've thrown it a certain distance. Right there, I've described two different distances, right? The fact that it goes from you to the rabbit is a certain distance, and the fact that it follows a path which may be a different distance. So there's a couple of different distances that you could talk about. You can talk about the fact that it slows down as it goes up and it speeds up as it goes down. You can discuss the amount of time that it takes. So all these are variables that describe the motion. It's not why the motion happened, but just that describe the motion. And the variables that describe the motion are called kinematic variables. Kinematics, right? Kinematic variables, or this is the kinematics of the motion. So notice when we're describing kinematics, we're talking about distances, we're talking about directions, we're talking about speeds, we're talking about time, and then the one other thing which might not be obvious is when we're talking about changes in speed, and changes in speed are accelerations. So those are the things that we use to describe the motion. Distances, displacements, direction, speed, time, accelerations. I just added the word displacements, which we'll define soon. So I want to differentiate, again, kinematics from dynamics. Dynamics is about the things why the motion happens, or details about the motion that don't describe the motion itself. Like, what is the energy? Let's say I'm throwing the rabbit a carrot, right? What's the energy of the carrot? What's the force that I threw the carrot? That doesn't describe the motion. Right? That describes sort of why the motion happens. It describes details of motion that you can't see. When we're talking about kinematics, about the things that you can observe about the motion just by watching it. So dynamics comes in later chapters. Our first couple chapters are about kinematics. So first, let's start with the distances, right? So we can define distance. Distance is a kinematic quantity, right? And the carrot follows this path, right? The carrot follows this path, and it goes a certain distance. Distance is the total path length, or the length of path traveled. So let's just take a different example, and let's just say that we're watching the path of our rabbit as it hops around the room. And so the rabbit sort of hops around the room. It starts from, let's say, point A, and it finishes at point B, right? So the distance is the length of the path that we've drawn, the length of the purple line. So notice that when we talk about the distance traveled, there's not really a direction associated with it. And when we talk about some of our kinematic variables, we're going to recognize that we can talk about a direction, right? That the bunny goes to the left or the bunny goes to the right. In this case, there's a net travel to the right, but at any one time, the bunny might be going up or down or left or right. And distance is a quantity that doesn't have a direction associated with it. But what are the units of distance, right? In MKS units, the units of distance, of course, are the meters. The next variable I'd like to define is the average speed. Average speed. Let's say that Bunny goes from point A to point B, a distance, whatever that distance is, in a time t. Average speed is total distance traveled over total time, right? Total distance over total time. I guess I said time t. So if we call the total distance d and time t a t, then it's distance over time. But it's total distance over total time. That's average speed. What are the units of average speed? Well, and I always put units in brackets. I try to always put units in brackets, so just get used to that. When I'm putting brackets, I'm just telling you what the units are. Distances are measured in, distances are measured in meters. Time is measured in seconds in the MKS units. So the average speed, the units of average speed are meters per second. I'll tell you right now that these are important if you understand the concepts, but we don't actually use these quantities in physics very much. There are other quantities we use much more. So one of the things you'll find is that we don't tend to represent these quantities with letters. I did represent distance with a big D and time with a T. We do use time all the time, but average speed and distance don't come up very often. Okay, what else can we measure? In order to talk about the next few things we're going to measure, we really need a frame of reference. In physics, the concept of frame of reference is extremely important. What do we mean by frame of reference? Let's say Bunny goes from A to B in the physics lab, right? In the lab. So we've got a lab, and there's the lab, and the frame of reference is the Bunny goes from the left wall of the lab to the right wall of the lab. So when we're talking about certain kinematic variables, we need to relate them to a given frame of reference, right? That we start from the left and we go to the right. And your generic frame of reference, it might be a lab, it might be a car. Car might be your frame of reference. You're measuring things inside a car when you're traveling, or your room, the room that you're sitting in is your frame of reference. But a generic frame of reference would be a coordinate axis, right? So a coordinate axis we can attach, for example, a coordinate axis, what I mean by it's a generic frame of reference is the coordinate axis can be attached to the lab, right? So in the lab, so we can have a coordinate axis, right? X-axis. And right, this is x equals 0. Then we can talk in more detail about where the Bunny is at any one time. In one-dimensional motion, we're going to generally use an x-axis as our frame of reference. So we say x equals 0, that's where we start, and x is where we end, right? Or rather than the left side of the room and the right side of the room. So we're going to use a numerical coordinate axis in order to talk about our motion. We are talking about one-dimensional motion, so notice that the Bunny moves in 2 dimensions. But when we're talking about one-dimensional motion, we are going to talk about just things that move either along the x-axis or along the y-axis, right? So we can have an x-axis and y-axis, but not both. And when we get to 2-dimensional motion, we'll talk about things that move both in the x and the y direction. But frame of reference is what's important here. That is what we're measuring things relative to. So let's say that we're just talking about one-dimensional motion, and we want to know where along the wall, right? The Bunny's running in 2 dimensions, but along the wall, where how far the Bunny goes in the x direction. And actually, let's just go ahead and rather than so here's something, right? Get ready for this. Rather than the x-axis running along the wall of the lab, let's just have the x-axis go from A to B. See if I can draw a straight line. There we go. That was kind of straight until the end. That's my x-axis, right? X-axis from A to B. So we can talk about the Bunny starting at x initial and finishing at x final. X equals 0, we set that arbitrarily, right? X equals 0, I set it outside the room, doesn't matter. Set it arbitrarily, and the Bunny starts at x initial and finishes at x final. Doesn't matter that it ran in 2 dimensions. I just want to know in 1 dimension how far the Bunny ran along the x-axis. And the first thing to note is, what is x called? X is called a position, right? It's a position. So the position is where you are relative to a fixed origin. That origin may be arbitrary, that you have fixed for yourself, you've just drawn your own axis, or it may be fixed for you, right? You might be told x equals 0 is at the left wall or whatever, or where the bunny starts is more likely. Position is usually written as an x or a y if we're talking about the position in the along the x-axis or along the y-axis, or z along the z-axis, or it might be just d. D often stands for, you think of it as distance, but it might just be along some arbitrary axis. We don't know if it's x, y, or z, or s, right? We use a lot of different variables for position. When we're talking about one-dimensional motion, we'll typically stick with x. We might use y, we might move along a y-axis, but we'll typically we'll define things in terms of x. But just recognize that we can change our position variable. If I call it x and instead I say, ooh, let's call it y, all the equations are the same, they just replace x with y everywhere. What are the units of position? The units of position is still a measurement of distance, because what the position is, remember, it is the distance along the x-axis from the origin to where you are, right? Where you are relative to a fixed origin. What that means is it is the distance along the x-axis from x equals 0 to where you are. That's your position. So the position is actually a kind of a distance, right? Again, we'll call it x, y, z, etc. Okay. So then we want to define displacement. It's another distance variable, displacement. Displacement is defined. Ooh, let's use the defined sign. Defined rather than equals is a triple equals. It's that kind of equal sign. The definition of displacement is x final minus x initial. That's the definition of displacement, which is called delta x. This is notation you have to get used to, right? So let's go back to the bunny. The displacement is simply the x final variable minus the x initial variable. So the displacement has something to do with this straight line distance, right? Rather than the path length traveled by the bunny, it's just this straight line distance. It's related to the length of that straight line that goes from xi to xf. So displacement is different than distance, right? Not only that, but notice that displacement can be a negative number. Let me go back. Distance is length of path traveled. That's always a positive number. Displacement can be positive or negative, because if x final is less than x initial, right? If the bunny is moving along the x-axis towards the origin, then the displacement is going to be negative. If x final is bigger than x initial, then the displacement is going to be positive. So displacement can be positive or negative. We're going to talk later about the difference between a vector and a scalar, and that's because the displacement is a vector. It's got direction associated with it as well as a length. So the displacement of the bunny in this case is xf minus xi, and you can see that the direction of the displacement of the bunny is along the positive x-axis. So it's a positive displacement. If the bunny then ran back to xi, it would have a negative displacement, because the final position would be xi and the initial position would be xf. Okay, so displacement is called delta x. Delta means change in. Change in. And we're going to use deltas all the time to indicate subtracting one quantity from another quantity, how the quantity changes. And again, MKS units, the units of displacement, is still a measurement of distance, and so it's meters, right? It's still a measurement of distance. It's the straight line distance. Well, it's a measurement of distance plus a sign, right? Plus a direction. It's the straight line distance from where you start to where you finish, and then it has to do with also the direction, whether you're going in the positive direction or negative direction. So I do want you to notice that distance is a different thing than position, which is a different thing from displacement, and you should be able to differentiate between them and understand their definitions. We did talk about average speed too. In the next lecture, we'll talk about average velocity and the other variables we talked about.